like this.
Do
Do you think it work now? Do you think it work now?
the entire thing.
Okay. Sorry. So as I was saying, if you multiply a column vector and a row vector with the same height of the column vector as the length of the row, you will get a scalar output. In this case, x1, y1 plus x2, y3 plus x3, y3, which is a singular number, which is defined as scalar. For a matrix multiplication, you have to make sure that the number of rows in the first matrix is the same as the number of, the number of, the number of columns in the first one is the same as the number of rows in the second one. My bad. And you get an output which has the same number of rows as the first one and columns of the second one. Yeah, that's correct. You have to keep note of this when you do matrix multiplication. So remember the diagram I showed you earlier and the formula I showed you earlier. If we remember the summation formula from the neuron diagram earlier, the one that's like bias term plus summation of wi xi I and blah blah blah, you can actually condense it using your knowledge of matrices and vectors, because the thing is, W is your matrix of weights, X is your matrix of inputs, and W by X is the dot multiplication of matrix multiplication. If you apply the activation function to this result, you will get the output of the neuron, sigma times V plus W multiplied by X. So for a layer of multiple neurons, this also extends to matrix multiplications, sigma times capital W times X plus V, where W is the weight matrix and V is the bias vector for the entire layer. Okay, so during the training process, we need to find a way to measure how well or how poorly our model is performing rather. And this is where the loss function comes in. So the loss function, also known as a cost function, or sometimes an objective function, will determine how poorly a model is performing by quantifying the difference between the model's predicted outputs and actual target values. So a lower loss will indicate better performance, as you would think, because there will be a less difference between your predicted outputs and the actual values. So as an overarching theme, like when different types of tasks use different loss functions, but as an overarching theme, classification tasks usually use cross entropy, and regression tasks often use mean squared error loss function. Okay, so for classification tasks, to be a little bit more specific, you can use, for example, binary cross entropy if you have two classes, and categorical entropy for multiple classes. In this case, what a classification task does specifically is that it predicts categories, which is why when you predict, like, for example, two classes with categories, you will have binary cross entropy. However, for regression tasks, where your model is predicting continuous values, you will usually use loss function to measure a numerical error between the predicted value and the actual value, which in this case, you can use an actual mathematical formula. There are three of them over here. For example, mean absolute, MAE, mean squared error, MS, and and root mean square error, RMS. Once we have a loss function to measure the performance, we sort of need a way to minimize loss during training. So this comes out with an optimization algorithm known as gradient descent. Gradient descent is a long sentence, I know, iterative optimization algorithm used to find the minimum of a function. What this means is that, like, iterative meaning that it repeats itself, and like optimization algorithm meaning that it works in a way such that it optimizes the function of the neuron. So in the context of neural network, the function that they're trying to find the minimum of using gradient descent is the loss function, the previous slide over here. So what the algorithm does is that it repeatedly calculates the gradient of the loss function with respect to the network's weights and biases, and then updates these weights and biases in the direction opposite to the gradient, if the gradient is like positive, which is the direction of steepest decrease of the function. So, wordy. But let's think of it this way. We're doing a physics problem now. What? It's like more like this is use your imagination and pretend like a big hilly landscape. And we're taking a ball and we're trying to get it to the lowest point possible on the hill. Because, like, for example, we're trying to find like the lowest gravitational potential energy or something, but then I guess it's a physics problem. So what you're gonna do here is you're gonna use your like secondary school first and second derivatives, and you're gonna try and find the like parts where your gradient is negative, or like to find a local minimum, we're going to write this one. Let's see. I don't know if you can see something. Can't see. Oh, here we are. Never mind. You cannot see. That's not matter. That's not matter. Okay, let's say we have a function y equals fx, arbitrary function. We're trying to find the minimum of it. So let's take the first derivative, y equals to dy over dx. Okay, when your dy over dx is negative, it means your function is going downwards. Yeah. Then you're going to take a second order derivative, which, okay, so when your first order derivative is 0, it either means you're at like the peak point or the lowest point, because the gradient would be 0 there. Yeah, so like here, 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 etc. Then you're going to do a second order derivative, which will help you find like if it's a minimum or a maximum. So if your second order derivative is positive, it means you're at the minima. That's great. Wonderful recap. But we're going to move on to the next section as well. So hopefully that little anecdote helps you understand a little bit more what I was talking about. Sorry. Calculating the gradient of the loss function for a complex neural network with many layers can often be challenging computationally, and this is where we bring back propagation in. So, back propagation is a method for efficiently calculating the gradient of the loss function with regards to the network's weights and biases. And it works in this way. We're working backwards to the network from the output back to the input, calculating the contribution of each parameter to the total loss. Parameter being like weight or bias, okay? And this allows us to determine how to adjust each weight and bias to reduce the loss as far as possible. So as we can see the same diagram from before, but we've added a little bit of the learning rate. So the new weights are the old weights minus the learning rate multiplied by the gradient of our loss function mentioned earlier. So back propagation allows you to have an efficient way to calculate this gradient here, the loss function gradient. And this process aids in improving the function. However, there are some issues that can arise, even though this is like pretty powerful. We have gradient descent like powered by back propagation. One significant problem is that it can get stuck in local minima. So if we look back at our little hill over here, we can see that there are some points that aren't truly the lowest part, but still have the same functionality as what I mentioned earlier with the formulas, that they are still minima, just not the global minimum. Okay? So, because the thing is, loss function can have many of these little local minima, and a gradient descent may find a local minimum that is not indeed the global minimum, which isn't actually your most optimal performance if you think about it in a way. You're trying to get it to perform the best of the best as possible. But another problem is that it can take a very, very long time on plateaus. Let's look at our friendly hill over here. Right off the screen, it's curving down really gently. It's not 0 yet, but like curving down really, really like gently. So that's a plateau. A plateau is a flat region in the landscape where your gradient is very close to 0. And so the parameter updates each time you iterate. They become smaller and smaller and smaller. And so the network learns really slowly, which may result in it getting stuck or taking a very long time to escape this plateau. So let's go back to our hill analogy once again when I explain saddle points. So a saddle point is also a type of tricky point to get across, because if you turn this funny shape that I've shown you over here, if you look at it from the side, it's like a sad face. If you look at it from the front, it's kind of like a happy face, because mathematically, at the point where I've highlighted with that big orange arrow there on the graph, the gradient is 0. But the thing is that from one axis, it's a local minimum, while on the other axis, it's a local maximum. So that's kind of a problem. Now, why is this a problem in deep learning? Because our optimization algorithms, like gradient descent, rely on gradients to decide which direction you move in. When the gradient is near 0, the algorithm will like mentally assume that it's closer to a signature, that the update becomes slow and slow. But the thing is, at a saddle point, just like with plateaus, you're kind of tricking your algorithm into thinking like it's stuck in like a flat spot, which isn't necessarily a global minimum. Like forget the global minimum. This isn't even a local minimum. This is neither a minimum nor a maximum. So, interesting note on this part, it's actually especially common in deep networks, which have high dimensional loss surfaces. In fact, researchers have found that saddle points may be far more common than local minima in some of these models. And that's one reason why training deep networks can be slow or unstable. Okay, sorry. So to address the issues of getting stuck in local minima or moving slowly on plateaus, there are some techniques. Like for example, here, you can use momentum. Momentum is an extent of the gradient descent algorithm, which helps in accelerate convergence and overcome these obstacles. So the core idea here is momentum allows it to relearn the old memory, remember its previous direction. So if you look at the formula, they were slowly adding more and more terms, other than the terms of the learning rate, also added a term about momentum, which you can see is using the old weights, and the weights even older than the old weights. You can't see, let me see if I can zoom it in for you. Over here. So if you remember the very first version of the formula just now, it was this part, which was new weights equals old weights minus learning rate multiplied by gradient of loss function. So now what we've done here is we've added another part of it, where we've got alpha times Wn minus Wn minus 1. Wn is your old weights, Wn minus 1 is the weights before the old weights, like older weights. And alpha is known as the momentum term, determining how much of the previous update direction, which was this. In the previous update, this was the new weight and this was the old weight. Now we're calling them old and older. So alpha, which is like a decimal between 0 and 1, kind of determines how much of the previous update direction is carried on over back to this one. Okay, sorry, didn't mean to change that yet. While momentum is helpful for helping speed up convergence and escape local minima, it does have its own problems as well, which one of the main problems is that it needs large oscillations, like kind of just repeats itself a little bit, and it can cause overshooting of the minima entirely, which can prevent the algorithm from settling at the lowest point at all. So you need to find the right balance for the momentum term, which is important for effective training. Another important concept here is known as batching. When training with a large data set, and computing the gradient over the entire is a little bit hard. But what we're going to do here instead is we're going to split the time frame into small little sections known as batches. And you're going to perform one step of gradient descent at every batch. So, there's a trade-off with batch size though. With a bigger batch size, there is more stable convergence. Is what we're trying, and then with smaller batch size, training is much faster since the updates are way more frequent. Even if each update is technically based on a noisy estimate. For classification tasks, especially when dealing with multiple classes, the raw output values from the final layer of the neural network will come in form of activation, as you could see in the video earlier. But for some cases, you need to convert them into probabilities. So this is the role here of the softmax function. Softmax converts activation into probability distribution. It takes a vector of the real numbers and like of the activation real numbers and transforms them into a probability distribution function, PDF, with all the values between 0 to 1. And if you sum up all those little values over there, the total of it will be 1, since it's a distribution of probabilities at each separate point. So as we can see, the graph on the left illustrates activation values for some random neural network. And on the right, you can see the probabilities of the, and lastly, there's the formula for softmax activation as well, which is heavy in numbers. So let's move on to section 3. After the end of section 3, I'll give you a short break. So just like bear with me a little bit. Probability distribution function. No problem. All right, so we're moving on to our next section over here, looking at some popular tools for deep learning models. TensorFlow, Keras, and also equivalents like PyTorch. Yes, these libraries will provide the necessary functions and structures to implement the concepts we've discussed, such as building neural networks with different layers. So the thing is, this is still a theory-based lesson. So of course, I highly encourage you to go home and try these on your own as well. But let's touch a little bit on how each model differs and like some ways you can build models yourself. So let's compare TensorFlow and Keras first. They're closely related, but they operate at different levels of abstraction. So TensorFlow is usually considered a low-level framework, providing lots of tools, like particularly suited for large-scale machine learning. While you can build complex models directly in TensorFlow, it can involve writing lots of detailed code for things like defining operations. energy computation graphs. However, Keras is considered as like a bit of a high level API because it's designed to be a bit more user friendly. It allows you to build an experiment with neural networks. Usually, it runs on lower level, like for example, TensorFlow. Keras runs on TensorFlow and can provide a simpler interface to define models, compile them, and train them with a little bit less code. There's also PyTorch, which is known for its dynamic computation graph, meaning that operations are defined on the fly, which makes it like a bit more intuitive and easy to debug. Let's also talk a bit now on TensorFlow and PyTorch. Let's talk about TensorFlow Hub and PyTorch Hub, which I do encourage you guys to look through. Yeah. So TensorFlow Hub and PyTorch Hub are both great resources for using pre-trained models. TensorFlow Hub is a library for publishing, discovering, and reusing machine learning models, which you can grab models for image classification, text embedding, with just a little bit of code. It's really handy when you want to use transfer, or you just want to use transfer learning and fine-tune a model without training it from scratch. Similarly, PyTorch Hub allows you to like load pre-trained models from GitHub repos. You can just call like torch.hub.load and then you put in your like repo, and well, you're pretty much ready to go. So it's good for you to test ideas quickly or to like benchmark certain things. So in short, TensorFlow Hub is a bit more structured, working well within the TensorFlow Keras ecosystem. You have like Keras running on TensorFlow, and PyTorch Hub is a bit flexible. So there are different ways to structure and build your neural network. Let's look at two of them. The first one is sequential API, which is the simplest way to build models that are a linear stack of layers. As we can see in the code on the left, you create a sequential model and you add layers one by one. So if you can see here, we make a sequential model, add like one dense layer with like the video activation, the second dense layer with the video activation, the third dense layer with sigmoid activation. You specify the number of neurons as well, 32, 16, and 1. But the functional API shown on the right is a bit more flexible. It allows you to define your models in a bit more complex ways, not just. So first what you do is you define your input layer, then you connect your like subsequent layers and like to the outputs of the previous layers. But you must you can define the flow of data explicitly here. As we can see, first one, the first element is text, second and third previous ones. Well, regardless of whether you use sequential or functional API, this is the general for building a model. The first step, we're using sequential API if you recognize it. But the first step is to build your model, of course. You define your layers and the properties by creating a sequential object and adding your dense layers to specified units and activation functions. Next, what you do is you compile the model, which in this case, you specify the optimizer like Adam. I think the intermediates might remember them mentioning Adam during the first workshop of the day. You specify your optimizer, in this case Adam, your loss function, in this case binary cross entropy, the one I covered earlier. So if anyone remembers, can you tell me what this thing is supposed to be? What is supposed to be estimating? What did I say? Loss cross entropy is the loss function for? Yeah. To be more specific, it's like categories and classes, but it's close enough, and then the last thing that you specify certain metrics, for example, in this case, like accuracy and the metric. And then the last one is what you do is you train it. So in this case, you provide training data, as we can see here, it's like X train Y data. You can also optionally provide validation data to monitor performance of unseen data during training. Then you need to specify your time frame within the blocks as well as your batch size. So as you can see, everything's pretty structured from start to finish. What you're doing is you're laying the foundations by building the network itself. Then you're combining with like your optimizer and loss functions so you can monitor its accuracy. And the last thing you're doing is training it to fit. Yeah. Let's take a bit of a 5-minute break over here. I'll resume. Sorry, one sec. Okay, I'll resume speaking at 4:30. You guys can go toilet or fill your bottles if you want. Just come back by 4:13. Thanks. It could be image off, not freeze. Can I freeze? It's fine. I don't mind. No, okay, sure, whatever. What happened?
Sure. Okay, this is not even a big issue. Okay. Then look at this. What the hell is this? It's like the entire thing is off, and the size is Keras plus PyTorch, right? So it should be one side, this should be one side. No. Then
No, it's TensorFlow versus Keras first, then both of them, then both of them versus PyTorch.
I'm recording.
They're recording.
Yeah. Oh, sorry. You can tell me if yes.
It's okay, doesn't matter. I'll ask them. Why am I having slide QA right now? This is hilarious. But okay,
It's like here right now. Like this when I'm seeing this first slide itself feels like, why is he trying to be so happy? We're supposed to be in the middle of the skips. Then she was like, hey, did she say Chris one is off also? And then she said,
can I ask you guys something about the slides?
yes, go ahead.
Why are some of the headers center justified? Why is some of the text, like some of the header text is center justified?
Right. I was just piece issue, so I just left centered it.
I
left justified it.
Okay.
Yeah, and so she was super like annoyed. Like, bro, if you have the time during their break, try to like check whether your remaining slides have this issue.
Just look through. Feel free to look through. The rest of the slides are not that many of them. These are all images stolen from them.
Yeah, she told me that okay, one of the things look very well similar.
It is like a lot of these are old diagrams.
Okay, this is not something that I'm going to be uploading to YouTube. Okay, let's not say this on YouTube.
Please don't.
Use a bit more left off.
This is where I've given up on justification.
This is 49, right? Remember 49? Oh, bro.
Every slide after this has a really justified. This should be hidden, by the way. One sec. Oh, okay. No. Go away. Go away. Go away. Go away. Go away. Go away. Okay. Is there anything else? Or is it just 49? 49
onwards.
It actually starts before 49. If you pay enough attention to the slides, you can see where it's coming. Yeah,
like it actually was
49 again.
Yeah,
So like what's the our teammate and yeah.
Okay, so what's the issue?
Teammate okay, take the attendance, sure. Take the attendance, no problem. Wait, take the attendance with her. I'm going to continue the majority of my back. We're going to continue, but before I move on to the next section, let's watch a little bit of the video I showed you earlier. One second, let me just. Okay, Okay, sorry, one second. Mike. Okay, so this marks the end of the math part. We're going to move on to a little bit more theory and pricing side. We're going to look at something called convolution neural networks. So, CNNs, also known as convolutional neural networks, are a specific type of feed-forward neural network. What a feed-forward neural network is just that one that goes in the forward direction from input to output. So unlike fully connected feed-forward networks, where every neuron in one layer is connected to every neuron in the next, and then every neuron in the next, and so on and so forth. CNNs, they use a special operation known as convolution, which I'll explain shortly. The key characteristic of CNNs is that they are excelled at learning features by something called kernel optimization, which refers to how the network learns small little filters, or also known as kernels, which sort of scan across your image to learn patterns such as edges, textures, or shapes. So if you remember the very one round video I showed you just now, remember how we talked about recognizing little parts of the numbers, like shapes like the loop with the number 9, or like little segments and bits of it, or like recognizing the edges of where a number ends by the activation. So these kernels are optimized during the training process to efficiently and effectively detect features in the image. So let's understand why CNNs are so effective for images, considering the structure of the image itself. At the most basic level, an image is a grid of pixels, and each pixel has a numerical value representing its color intensity. So we can see here this cute image of a dog. You can zoom in and see each little pixel of the grass or of the fur. So for color images, the structure is slightly more complex. Instead of a single grid of pixels, a color image may typically have multiple channels. In this case, the RGB color model has 3 channels, and each channel has a value of as an intensity value between 0 and 255, for example. So CNNs are designed to process multi-channel inputs, which applying the same convolutional kernels across all channels, or different kernels with different channels sometimes, so that they can learn important features. The problem with using a regular multi-layer perceptron is that, like, if we feed an image into a and then it connects itself to all the neurons there, it sort of has to be flattened to a one-dimensional vector by the end of everything. As you can see, for example, let's have a 2x2 image. You assign it to one input neuron for each colored square. But as you continue to process the information, it gets into this one single length vector, which ends up making it lose something called like spatial features, or like its relationship with regards to where it is in the space. Losing the spatial context makes multi-layer perceptrons way less effective at recognizing patterns that depend on the arrangement of pixels. Like, let's go back to the example again of determining at the edge of like the number 7, for example. Where does the number stop? Where does the number start? Determining the edges of an image or the edges of a number or the edges of reading anything kind of require you to know in context where certain things are, where certain pixels, where certain pixels of the image are positioned with respect to other pixels. So we're going to look at the 3 layers in a CNN. The convolution layer, the pooling layer, as well as the classification layers. There are 3 of these, yeah. So these layers are responsible for determining local features of the image. Convolutional layers perform something called the convolution operation, which applies learned kernels to the input, also known as those like little small filters, to create something called a feature map. So the convolution layers are most responsible for detecting local features in the image. Then pooling layers are used to reduce the spatial dimension, which in this case are the width or the height of the feature maps, while still retaining important information. It's like you can kind of think of pooling in a way like whenever you, like, for example, you carpool with your friends, all of you are in one car. So you're kind of reducing it. So this helps to reduce the number of parameters of computation and also makes the network robust to small variations in input position. Common pooling operations will include max pooling and average pooling. I'll go into global average pooling soon. And finally, the fully connected layers, which are similar to layers of P, are, as the name suggests, fully connected, taking the flattened output from the convolutional and pooling layers and using it to perform the final classification or regression task. Let's go back to the convolution layer real quick. Convolution is described as a specialized type of linear operation, which in the context of CNNs, it involves sliding a small matrix, known as a kernel of filter, over the input image or the feature map and performing something called element-wise multiplication, summing the results up. And this highlights specific features in the images, which in this case can be like an edge or a corner, depending on the values of the kernel. And convolution is combined with activation functions and pooling layers in order to process the image and extract infinitely complex features, which ultimately leads to classifications with their associated probability. So as you can see here, convolution converts all of the pixels in the vector field into a single value. And it outputs at the end, like it just outputs a vector at the end. Yeah. So, like about flattening. After the convolutional and pooling layers, the output is a multi-dimensional structure known as feature map. And this feature map represents all the learned features which are extracted in the input image. To feed this feature map into a fully connected layer, like which is similar to MLP, it needs to be converted to a one-dimensional vector. Flattening does exactly, except it converts it into a one-dimensional super long vector by unwinding it. You can see like unwinding it in a way. So, but a consequence of flattening is that a very large number of inputs can come into the multi-layer perceptual layer, fully connected layer, which increases the number of parameters in the MLP and can lead to sort of computational cost or potential overfitting if not managed. In this case, overfitting is making it extremely specific to only one use case, which means your neural network is only really good for one thing at the end of the day. Which, especially for something that's really cost high, you kind of want it to have like multiple purposes. So overfitting isn't necessarily a good thing. However, as an alternative to flattening, a technique that's known as global average pooling is used. Instead of converting the entire feature map into a singular vector, global average pooling takes each of the feature maps and calculates the average of all of its values. So if you have like C number of feature maps, this results in a vector number C. As you can see here, let's assume each of those with one feature map, and you have C number of feature maps all the way. You can think of them as like, let's say I have a whole bag of Pringles, like a whole can of Pringles, and like each Pringle is, in a sense, a feature map. So what we're doing is we're kind of polarizing it, and we're just going to make it into a which is the average of it. And at the end of the day, you're going to have one singular column vector with each value representing each feature map. So global average pooling significantly reduces the number of parameters compared to flattening and can act as something called a regularizer, which helps sort of generalizing everything, which can make you use your model for more things. Next, as these neural networks get larger, sometimes training can be challenging due to a phenomenon which I will not be covering, but if you want to Google it, it's called internal covariation, where the distribution of inputs to a layer changes as the parameters of the previous layers are updated. It's called this because if you think about it, like we change the previous layers, your next layer will internally shift because it's connected to the previous layer and it varies a bit. So there's something called batch normalization, which is a technique used to address this. The batch normalization normalizes the inputs to one layer, forcing the mean of the values to 0 and the standard deviation of the values to 1. This is typically obtained via a moving average during training. And the formula is actually, batch norm equals x minus sigma beta. Yeah, wonderful. Where mu is the mean, sigma is the standard deviation, and the other two are learned parameters allowing the network to scale and shift the normalized value if necessary. So by normalizing the inputs, batch norm makes your training process more stable and also allows you for higher learning rates. Importantly, it enables each layer to learn more independently, as changes in previous layers have less impact on the input distribution of subsequent layers. Another important technique for training neural networks, particularly for preventing this problem I mentioned earlier, overfitting, is known as dropout. So in dropout, you randomly select certain neurons to be dropped out of your computation, which prevents like over-specificity with your neural network and improves generalization, allowing you to have way more use cases. So as we can see the diagram here, we keep using this diagram over here. So you can see certain random neurons from the hidden layers have been crossed out. Yeah. This ensures that no single neuron can rely too heavily on the output of any other specific neuron, which helps prevent like overfitting, as I mentioned before. So let's zoom out and take a final look at the overall structure of a convolutional neural network. As we can see, the network input, which is typically an image, is processed through several hidden layers. These hidden layers usually consist of alternating like convolution and pooling layers, which extract and process spatial features. And after those two, the data is often flattened or uses global average pooling. And passed into a standard multi-layer perceptron. So with this MLP, it acts as a classifier or regressor, again, depending on what you're doing with it, taking these learned features and producing the final image class prediction. So the CNN leverages convolution and pooling to effectively process your grid-like data, for example, with images, before using the traditional dense layers for the final output. Moving on to next section, we are going to explain recurrent neural networks, or RNNs. Unlike the feed-forward networks we've discussed so far, MLPs and CNNs, which work from start to finish, from input to output, RNNs are actually designed to handle sequential data, where the order of your elements matters greatly. So here's a quick introduction. RNNs are specifically trained with sequential, also known as time series data, creating an ML model that can make sequential predictions based on sequential input. In this case, in your input, in the data, the order of your data points is really important, such as text, speech, or sensor readings, which occur over time. So how they do this is they maintain an internal state in memory, capturing information from previous elements in the sequence, which influences the processing of the current element. Common use cases for RNNs include prediction based on past patterns and solving ordinal and temporal problems, such as language translation, NLP, which is natural language processing, speech recognition, and image captioning, all of which involve processing sequences of data. So remember the example from the video earlier where he's trying to recognize a word by splitting it first into letters, then forming its syllables. Then you also have to consider the time, the temporal position of each syllable in order to make sure. For example, if you're recognizing the word recognition, you need those syllables to be in that specific order. Here's where the time position matters greatly. So, compared to traditional deep learning networks, which assume inputs and outputs are independent of each other, they process each element in isolation. For example, if we gave our traditional DL network a sequence of words, we treat each word independently without considering the context provided by the words before, shown in the top diagram where inputs are processed separately. An RNN, however, works a little bit differently. It's designed to take information from prior inputs to influence current input as well as the output that's coming out from it, which is achieved through a recurrent connection. Hence the name, which allows information from the previous step in the sequence to be fed back into the network during the current step. So let me give you another example of why this is so important. Let's imagine, for example, if you guys know slang versus the official meaning of a word. For example, that's sick can mean it's so cool versus I'm sick can mean I'm actually sick like I am right now. You have to consider the words that come before it as well. So in the recurring neural network, you have to feed in the previous words information into the current one as well, considering it when being processed. Sorry. However, do note that while feature events can be helpful in determining the output of a given sequence, they cannot be accounted for in unidirectional RNNs, where it just takes the past information. You'd have to use more advanced RNN architecture to process sequences in both directions. So let's compare and contrast a little bit between CNNs and RNNs. As I've explained before, CNNs are designed primarily for spatial data, like with images, where the position of something relative to another is really important. Using convolutional layers to scan input data in small patches and capturing details like edges, textures, or shapes, corners, patterns, such like that. CNNs are translation invariant, meaning they're really great at recognizing patterns, regardless of their exact position, which is why they're used for image classification, object detection, or even something like medical imaging. On the other hand, recurrent neural networks process input one step at a time while maintaining a memory of past inputs through hidden states. This makes them ideal for problems where order and context matter. Time series forecasting, speech recognition, and other things like that. But both of them have their own limitations. CNNs struggle with sequence-dependent data because they don't have memory, or in a sense, a series of time. While RNNs, while great at handling their sequences, can suffer from vanishing gradients, which makes them hard to train on long sequences. Although there are some variants that can help fix that. If you want, you can Google LSTM. Like there's the letter L, letter S, letter T, letter N. So, sum it up a little bit, CNNs are great at extracting spatial features, especially in images. The RNNs are better for extracting temporal or contextual patterns in sequences. They both serve many different purposes, and in certain models, like for example, with image captioning or video processing, you may need both of them at the same time. They're even combined. Let's think about how we can use them, for example, in image captioning, where your CNN will capture the image features, and then at the end, your MLP will extract, like will output what like it thinks the image is with a certain amount of confidence. And the RNN, using the temporal data from the past patterns, can identify the overarching patterns as we see. So for example, let's think about it processing a video. It sees like a duck or something, and it's moving across the screen from left to right, and then right to left or something. Your CNN would recognize the fact that it's a duck, and then your RNN would process the pattern of it, blah blah blah, so on and so forth. We're in our last section now. Bear with me a little bit longer, because I'm just going to talk quickly about ethics. Whenever you do something with a DL model, it's also important to consider ethical considerations with the development and deployment, since with great power comes great responsibility, and we need to think critically about it. So, particularly in AI safety, here are the following things we need to consider. We need to encourage fairness and impartiality in decisions made by AI systems, which can avoid inherent biases, for example, that may be in their data, which can lead to discriminatory outcomes. There also needs to be some form of transparency in how the AI proceeded to get to its sudden decision that it made or the conclusion that it came to. It also needs robustness to work in unfamiliar situations, which is exactly why overfitting is such a bad problem. We need it to work in an ever-changing dynamic environment. So in this case, something like generalization is pretty useful. And we also need to calibrate the model often. The model needs to demonstrate when it's unsure about its predictions. Alongside these two safety concerns, we've also got some big questions to think about. How does deep learning truly work? Understanding the internal reasoning process of complex models is still an active area of research. And we still need to decide, should we allow DL to make real-world decisions, since we don't entirely know their reasoning? We need to carefully consider our data as AI systems become more integrated in our lives. Now, I'm gonna get you guys to play a quick Kahoot quiz, and I have prizes over here. But the thing is, the prizes are team-based. Since Kahoot kind of has a member limit, I'll need you guys to do this in your teams if possible. If you're an individual, just do this individually, it's fine. Okay, give me a sec. I was creating the whole guys. Okay. Is anyone listening? Okay. I'm really talking about that. Because I might sorry. Actually, let me see if I can do it at once. Let's try that. What idea? Hmm. If you guys join the first one, please don't join the second one. There's running two of them at the same time. It's how we're gonna go. Okay? Please don't join if you run the when this one is participant limit not at the same time. Not ten seems to be okay, question mark. I'm gonna start now. Is that okay? Yeah. Okay, I'm gonna start. Before I start, I would recommend you focus on your phone, the questions on your phone. Don't look much at the screen in case both of them randomize the questions. Let me see if I can set that. Okay, the question order is not randomized for both of them. So ideally, you guys should be getting the exact same questions. All right. I'm gonna start both, okay? Are they all working? Log in. If you guys remember, right, 10H is the one from -1 to 1. Sigmoid is from 0 to 1. If you look at the y-axis, this is so fun. It's okay, guys. It's okay. There's more questions. If you remember, the step function moves to the left or the right, changing its position. Now, guys, we're about 1/3 through. Push through, guys. select for cost money. It costs money. My bad. My bad. My bad. Gambling. All in. Bas, sorry. That's why I'm presenting on it. What more questions left? Last question, guys. Second one. So the top three, top three scoring means that I1 with 12,577 points, I3 with 12,371 points, and B29 B29. You guys come on stage. Okay, you guys, yeah, socks and Hershey's. Wait, one sec. Sorry. I only have one Hershey's, but I have plus socks. So please, you can get one pair of socks. Here you go. And here's the Hershey's for you guys. You can you have one. Do you guys, do you want to hold them? You guys can stand. Go. Do you want to stand in front, like closer to the front? Okay, please. And team I3, come to stage. I3. I3. Everyone come to them. Woo! You guys also get some. The first prize is number of something. So yeah, here you go. Okay. Okay. Only person from his team to be here right now is I1. You guys can't believe it. This is okay, wait, skip a little bit, guys, cause one sec, I'm gonna close this. Bye bye. Thank you so much for listening to my presentation today. I hope you guys got wonderful takeaways. Thank you.